This is 3.4 Related Rates worksheet. I'm going to go through the explanation of each of the problems. In question 1, it says a small balloon is released at a point 150 feet away from an observer who is on ground level. If the balloon goes straight up at a rate of 8 feet per second, how fast is the distance from the observer to the balloon increasing when the balloon is 50 feet high? So I'm going to draw a right triangle and label this as X, and this one is Y, and then the hypotenuse as Z. So since it says that the small balloon is released at a point 150 feet away from an observer, that would be this length right here. So X is going to equal 150. And that is actually going to stay constant. If the balloon goes straight up at a rate of 8 feet per second, so that would be dy dt, and that's going to equal 8. How fast is the distance from the observer to the balloon increasing when the balloon is 50 feet high? So then I'll be looking for dz dt, and that's when y is equal to 50. So I'm going to first of all start off with my Pythagorean theorem. X squared plus y squared is equal to z squared. And since 150 is a constant, I'll just put that in before I take the derivative. So I have 150 squared plus y squared is equal to z squared. Then I take the derivative with respect to time. So 150 squared will drop to 0. And then y squared is 2y dy dt. And that is equal to 2z dz dt. So I know what dy dt is, and I know what y is, but the information that I don't know is z. So I'm going to use the Pythagorean theorem, and I'll use 150 squared plus 50 squared, and that is equal to z squared. And so z comes out to square root of 25,000. Okay, now I can plug that back into this equation, and I'm just going to cancel out the 2's. So the 2 can cancel out here and here. So then I get 50 times 8, and that is equal to the square root of 25,000 dz dt. And then when you divide through by 25,000 with 50 times 8, you get 2.529, and the units on that would be feet per second. For question 2, water is pouring into a conical cistern at the rate of 8 cubic feet per minute. If the height of the cistern is 12 feet and the radius of its circular opening is 6 feet, how fast is the water level rising when the water is 4 feet? So I'm going to first of all start off with the volume of a cone, which is 1/3 pi r squared h. And then the other information is dv dt is equal to 8, since it says that the water is pouring into a conical cistern at the rate of 8 feet per minute. Then if the height of the cistern is 12 feet and the radius of his circular opening is 6 feet, so that would be something that is not changing. So h is equal to 12 and r is equal to 6. And then dh dt is what you are looking for, because it's asking how fast is the water level rising, and it's when the water is 4 feet. So I'm going to use the height and the radius of the cistern to give me a relationship here. So I have r over h is equal to 6 over 12. So I draw my cone. So this is the height of the cistern, and this is the radius, and this is the amount of water that's getting filled. So h for the water and the radius for the water, that is what is going to be changing. So I cannot put in any numbers for this. So solving this, I reduce 6 over 12 to 1/2, and then I solve for r, and I get r is equal to h over 2. Now I take this h over 2, and I'm going to substitute it back into my volume formula. So pi over 3 is from this, and then r is h over 2, and that gets squared, and then it's times h. So put together all of the the constants. So that would be pi over 3, and then in this denominator, since it gets squared, it's a 4. So this will come out to be pi over 12, and then you have h cubed. Okay, so now I'm ready to take the derivative with respect to time here. So this will be dv dt, and that is equal to bring down the 3, so that gives me pi over 4 h squared, and then I have to take the derivative of the inner, which is dh dt. Okay, now I substitute in all the information from this side right here. So dv dt is equal to 8, and then h is 4, so it'll be pi over 4 times 4 squared, and dh dt is what I'm looking for. And so simplify this, and I get 8 is equal to 4 pi dh dt, and then divide through by 4 pi and reduce, and that gives me dh dt is equal to 2 over pi, and the unit on that would be feet per minute. Okay, for problem 3, oil spilled from a tanker spreads in a circle whose circumference increases at a rate of 40 feet per second. How fast is the area of the spill increasing when the circumference of the circle is 100 pi feet? So I'm going to first of all start off with the circumference increasing at a rate of 40 feet per second. So that would be dc dt, and that is equal to 40. And then the question is asking how fast is the area of the spill increasing. So I need to find dA dt when the circumference is equal to 100 pi. So using this formula, I can put in circumference in general is 2 pi r. So if the circumference is 100 pi, then putting c in 100 pi in for c, and then setting that equal to 2 pi times r, it gives me a radius that is equal to 50. Okay, so I want to find the area, and so the area formula for a circle is pi r squared. So if I take the derivative of area with respect to time, I get dA dt is equal to 2 pi r dr dt. Now I don't have a dr dt, but I do know the circumference formula, and I do have the circumference rate. So I'm going to use circumference is equal to 2 pi r, and then take this derivative. So dc dt is equal to 2 pi dr dt. So since they tell me that dc dt is equal to 40, then I can substitute that in here, and then is equal to 2 pi dr dt. So then I get dr dt to equal 20 over pi. So with this information, I can substitute it back into the dr dt from this formula. So I get 2 pi times the radius is 50, and that's found by what I stated right here. And then multiply that by dr dt, so that's 20 divided by pi. The pi's will cancel out, and then it's 2 times 50 times 20, so dA dt is equal to 2,000. And since the unit for area is square feet, and the unit for time is seconds, it would be 2,000 square feet per second.